So today it's a very great pleasure to have Jean-Philippe Rolin, maître de conférence at the University of Dijon. And the title of the talk of today is Recent Example in o-minimality. Yes, you can start.
Okay, so many thanks to all of you for this invitation. It's a pleasure for me to speak to this gatherings of various universities. I hope I didn't make mistakes in the acronym I used on this slide. And so, as you can see on this slide, for the purpose of my talk is to first remind you a few things about o-minimality and o-minimal structures for those of you who would not be so familiar with the topics, and then to show a recent result which has been obtained with me and in collaboration with Tamara Servi from University of Paris, and Patrick Speissegger from Hamilton University McMaster University in Hamilton, Canada. Okay, so let's start. So let me first give you an introduction on this general topic. I'm sorry, probably some people in the audience already know well these kind of things. I'm very sorry for them, but I decided so that everybody can follow to remind a few basic things on the topic.
That's a good idea.
Okay, great. Okay, so I think in my view the main point of o-minimal structures is to generalize the well-known real algebraic and real analytic geometries using functions which may not be analytic. So the very basic ideas here can be found in a wonderful text by Grothendieck called Sketch of a Program, Esquisse d'un Programme in French, which has been written by him between 1972 to 1984. It's programmed to be hid at French CNRS, which he was in 1984. So in this text, he introduced the notion of so-called tame geometry. So let me quote a few words from him to present the bottom of his ideas here. So a sentence that you can read in one chapter of this program is the following one. He says that, we may agree or not, by the way, but he says that general topology has been developed in the 30s and 40s by analysts in order to meet the needs of analysis and not for topology per se, i.e., the study of the topological properties of the various geometric shapes. So according to him, analysts in general are more interested in wild phenomena than in, let's say, tame or normal phenomena. So his program, part of his program, is to go in another direction. So on the contrary, precisely, he suggests to build what he calls a tame geometry. So according to him, the way we can do that is to build this tame geometry can be obtained by extracting the appropriate properties of real analytic sets, which would make it possible to use these as local models for a notion of tame space, whatever it is. For example, among all the possible properties we could have taken from real analytic sets, he suggests to impose a triangulability axiom. Why not? And according to him, this would produce a vast infinity of tame theories, all contained in what he pretends to be the vastest of all, that is what is called now the category of global subanalytic sets. We will see later that this program is not entirely correct, and I will explain you why. Well, it is widely admitted that the best answer to this program is contained now in the notion of o-minimal structure, which has been introduced by Van den Dries in 1984, not as an answer to this precise program by Grothendieck, but as an answer of a question more related to actually logic and model theory. But it turns out to be the perfect, in my opinion, and not only mine, but in the opinion of many people, the perfect answer to this program of Grothendieck. That is how to build a tane geometry. So now it's time for me to give you a precise definition of what is called an o-minimal structure. So you consider a collection of function f of real function which are total function that is defined on the total space Rm for various integer n. So I'm not asking anything on this class of functions. I'm not even asking to work with algebras of function or whatever. You just pick a collection of functions, which can be a single function or an infinity of functions. So let me call f, big F, this collection. So the first definition is the following one. You say that a set A, which is a subset of one Euclidean space Rn, is definable in the structure Rf, which is usually denoted by R and with these symbols, meaning that we are extending here the the structure of ordered ring or ordered field on the reals by precisely the function which appear in this collection, the function f. So again, we say that a set is definable in this structure if, well, A, the set A belongs to the smallest collection of subsets of the space R, R2, R3, and so on, which, well, first, so the smallest collection which first contains the graph of the sum and the product and all the functions in F. So here you see that we are enlarging the semi-algebra or the algebraic structures on the reals by the functions on this of this collection. Second, this collection must contain all diagonals, just for convenience here, in xi equals xj contained in all the Euclidean spaces. And finally, this collection has to be closed under Cartesian products under all the Boolean operations, meaning union, intersection, and taking the complement. And finally, it has to contain the images of projection maps x1, xm plus 1 towards x1, xm. So this is what means to be definable. A set is definable if it is contained in the smallest collection of sets satisfying all these properties and containing the graphs of the function of my collection f here. Okay, similarly, a function f is said to be definable in the same structure Rf if its graph as a set is definable in this structure. Okay, so we know now what is a definable set and a definable function. An easy exercise that I'm not going to prove here, but it's very totally straightforward, says that actually where does the word definable is coming from? Well, it's coming from the fact that another way of considering such a set is to say that a real number or tuple of real number is an element of a set if it satisfies a first order logic formula involving quantifiers and quantifiers, existential and universal quantifiers acting on the real numbers and containing only the classical logic connectors and this operation plus product, the equality, and the symbol of functions for this category of function. So it's totally straightforward to prove that these two ways of considering definable sets are totally synonymous. By the way, I didn't say that, but of course, do not hesitate to interrupt me if I am not clear here or there. Or if I am too obvious for you, I mean, if you are already familiar with these notions, I can be faster at the beginning. Just tell me. A little remark, say that actually the family of definable sets is quite obviously closed under a lot of basic operations, such as, well, of course, finite union. It's more or less by definition here, because you will consider a collection of sets which is closed under Boolean operation, and similarly topological closure. I mean, if a set is definable, its topological closure is definable as well. That's quite obvious if you remember that you can define the topological closure via a first order logic formula for every epsilon and so on. Well, it is definable because you can define it by a logical definition with the same language. Okay. A more subtle definition is that one. So we say that the structure. Yeah.
Just a question. The topological closure means that you add infinite union.
No, it doesn't mean that. I mean, by topological closure, I mean just what we call in French the adhérence of the set.
Okay.
So it is A bar. This is what I call topological closure. Okay.
So you use the usual topology of Rn, and
absolutely, yeah. I consider the space R and Rn as a Euclidean space, and I work with the usual topology on them. So when I say topological closure, I mean in these topologies. Okay. The next definition is that one. We define the structure to be. We say that the structure is model complete if the operation of taking the complement in the Boolean operations here is superfluous. So what does it mean exactly? Well, a way of considering all these family of definable sets, among these family, the elements of such a family, you have what I could call the semi-F analytic set, meaning a set defined by finitely many equalities or inequalities satisfied by functions of my collection F here, and possibly using the product and the sum and product. So we can define, similarly as you would define a semi-analytic set, you can define a semi-F analytic set here. And similarly again, you could define a sub-F analytic set as being a projection, a linear projection of a semi-F analytic set. Well, we say that the structure is basically, that the structure is model complete here if, to say the things shortly, the complement of a sub-F analytic set is again a sub-F analytic set. That is, that model complete here can be understood as literally synonymous in this framework to satisfying a Gabrielov property of the complement. Am I clear? So we call that model complete. And finally, so the main word of this definition is what does it mean for a structure to be o-minimal? So the letter O here means order. So we could say order minimal. So the structure is called o-minimal if every definable subset of the real line, only the line and not all the spaces, which is definable in the structure, is a finite union of points and interval. Okay, so to be o-minimal, a structure actually has only to satisfy such finiteness property a priori for the definable subset of the line, which is, so in this page, in this slide, so you have two things. First, well, a structure contains a lot of sets, of definable sets. As you can guess, all the sets you can define by first order logic formula using the element of the collection F. But at the same time, the notion of o-minimality looks quite, if I can say so, small, because it speaks only of the definable set of the real line. We will see that this definition here is the perfect answer to the original program of Grothendieck that I presented in the first slide. Okay, so if there are no questions here, a little remark before I go to the next slide. Actually, the definable set of the real line is not such a small family of sets, because to obtain a definable set of the real line, you have to go through the entire structure, starting from a set belonging to Rn, then you project it, you take the complement, you project it again, you take the complement again, and again and again. So, and you go at the end, you reach a subset of the real line, meaning that actually, in some sense, we could say that the definable sets contained in the real line carry all the complexity of the complete structure, in some sense. So this is why this definition, which might look very simple and which speaks only of the definable set of the line, in some sense speaks of the entire structure as well. So let me make this statement more precise here by showing you some beautiful properties satisfied by o-minimal structures. So all of them can be found in the book written by Lau van Endries himself in 1998 called Tain Topology and O-Minimal Structures. So let me list some of these properties. So again, I am assuming here that I'm working with an O-minimal structure called RF. Definable, the word definable here will mean definable in this structure. Okay, so if you consider a definable set A contained in Rm, first property, A has finitely many connected components. That's a result. Remember that in the definition, we impose this finiteness property only for the definable subset of the line. So actually, this finiteness property holds for every definable set. More precisely, so let me draw a kind of a picture. Imagine that you have a set which is contained in the Cartesian product Rm times Rn. Okay, so let me draw a set which has to be definable here, something like that. So this is A. So assume that A is definable in the o-minimal structure Rf. So the statement says the following: if you consider any element y of the basis here, that is which is here, C here, to consider any element C of the basis, and you consider the section over C in A, that is this set here, which projects over C. Okay, so the second property says that there exists a uniform down independent of C of the number of connected components of such a section. So that's another beautiful property satisfied by any definable set of in an o-minimal structure. Okay, so the statement is here. Second property, well, for any k, a definable function in one variable from R to R is piecewise ck. Of course, by piecewise, I am meaning here on finitely many pieces, which could be point or intervals. So on. So I guess the statement is clear. And finally, final property satisfied by definable sets, we have what is called the CK cell decomposition. So what does it mean? consider an integer k, and then for every definable set, there is a cell decomposition of the space, of the total space, which contains this definable set, which is adapted to the definable set, meaning that the definable set is a finite union of cells, and the complement of the definable set is also a finite union of cells of this decomposition. And you have plenty of such wonderful properties. You probably recognize here a lot of properties you are familiar with, which are satisfied by the objects of real algebraic or analytic geometries. So they are satisfied as well by any definable set of an o-minimal structure. Again, we are literally here not following, but we are satisfying step by step the original program of Grothendieck here. And all this is very tame. And we have also the thing that precisely Grothendieck wanted to add as an axiom. It comes here as a property, what is called the definable triangulability theorem. Okay. Now,
just two questions.
Yeah.
What is the triangulability?
Well, triangulability means the classical decomposition of a set via the simplicial objects.
Okay, I understand.
But here we are imposing that these sets, the element of this simplicial decomposition are definable, so they all belong to the same structure.
Thanks.
A little remark, by the way, to complete my answer to Kevin. Here you see that we are speaking of CK, cell decomposition. So for any K, we have the property of CK cell decomposition, right? So I guess a natural question here, does it imply that we have the property of C infinity cell decomposition? And the answer is no. And there exist examples of structures for which you have CK cell decomposition. I mean, when I say structure, I mean o-minimal structure, for which you have CK cell decomposition, but no C infinity cell decomposition, meaning that the simplicial objects which appear in the decomposition are definable and bounded by graphs, say, of CK function, but not C infinity function. Okay, so these summarize some of the beautiful properties satisfied by the object in a tame geometry, that is in an o-minimal structure. So it's time now to see a few examples. So these are what I would call the historical examples. Okay, so I'm going to define structures by considering the initial collection of functions that we are adding to the structure of real field of the real numbers. So first we had nothing. Assume that F is empty. So we have nothing, meaning that the corresponding structure is made only by the so-called semi-algebraic set. So here, definable means semi-algebraic, right? Why is it o-minimal? It is o-minimal by Tarski's elimination, which says that the projection, the linear projection of a semi-algebraic set is semi-algebraic as well. So that's the most basic example. I would say the smallest collection. Well, it might not be the smallest because let's say, yeah, the smallest collection o-minimal structure that we can imagine. So remember that the one thing which has been raised by Grothendieck at the beginning was the notion of a vastest collection, which is another problem. Okay, the second example is an important one. Consider for big F the set of all functions f from Rn to R, which whose restriction to the unit polydisk for on dimension m is real analytic, and which are, I mean by that we are considering functions on a small neighborhood of the unit polydisks, and on this open neighborhood, they are analytic. So I just consider the restriction to the open polydisk, and I extend them by 0 identically outside the polydisk. These functions are classically called restricted analytic functions. So again, these functions generate a no-minimal structure. So here, the structure is usually denoted by R sub n, or R sub an, as you can read here. And a definable set here is what we call in analytic geometry globally a subanalytic set. So why is this structure o-minimal? It's quite an immediate consequence of, let's say, Lojasevic theory of semi-analytic sets and a wonderful theorem due to Gabrielov, which is called the theorem of the complement, and which says that the complement of a subanalytic set is a subanalytic set as well. Okay, these are the two historical examples of o-minimal structure. And this is exactly the kind of thing we want to generalize by considering different types of functions. So let me show you now a more recent example, which is quite remarkable. Assume that you have in hand an o-minimal structure Rf. Okay, so you already have, for example, one of these two structures. Then what is called the Pfaffian closure of Rf is also a no-minimal structure. And this is a beautiful result due to Patrick Speissegger in 1999, if I'm correct. So very briefly, what is meant by Pfaffian closure of a structure? Well, you consider, so you have to introduce new sets or new functions. I mean, you can introduce function by introducing the characteristic indicatrix function of sets. Okay, the sets that you are considering here are so-called non-spiraling leaves of codimension 1 foliations defined by one differential forms whose coefficients are C1 definable function of the original structure. That is, you have omega, the differential form which define the foliation of codimension 1, could be the sum of A1 dx1 plus etc., where all the coefficients A, J are definable in Rf. And you assume that you work with so-called, I'm not going to define it more precisely, non-spiraling leaves of the foliation. So you intersect such non-spiraling leaves. Well, this picture also shows that my name is not Leonardo da Vinci. It's another thing. Okay. Anyway, well, the structure generated by these objects, that is solution of differential equations or leaves of foliations, is o-minimal as well. So you have now a big extension, for example, of the two original structures by a fantastic collection of sets. So the fact is that this collection of sets satisfy all the beautiful properties arising in analytic geometry. So we are now really in the deep parts of Grothendieck's program here. Okay, another example, a statement which says that if a structure is o-minimal and model complete, remember that model complete means satisfy a Gabrielov property of the complement. The complement of a sub thing is also a sub thing. Well, if a structure is o-minimal and model complete, then its exponential closure is also o-minimal and model complete. And this is the result by Van den Dries and Speissegger. So what does mean exponential closure? This notion will be important in the following. Well, an exponential closure means that you consider the structure generated by f, so the collection of functions we had here, and also the exponential, the total exponential function, which is not a restricted analytic function, because a restricted analytic function has to be extended by 0 outside of a polydisk. It's not the case here. I am considering the total exponential function on the reals. For example, the logarithm function is definable in this structure, obviously. Okay, so if a structure is o-minimal and beautiful, model complete, then the exponential closure is as well o-minimal and beautiful. Okay, that's all for the classical examples. So now I'm going to, let's say, my real topic in this talk, which is the study of two classical functions from the point of view of o-minimality. That is, the question has been asked quite early in this history: how do all some of the beautiful functions arising in number theory or analysis or functional equations and so on, how do they behave from the point of view of o-minimality? Could they, for example, be definable in some o-minimal structures? And as you probably guess if you read my abstract, I'm going to work more precisely with the classical zeta function and the gamma function. Okay, let's start with the zeta function. Of course, here I'm going to restrict the zeta function to a real interval, 1 plus infinity. Well, a little remark here. Everybody knows that the zeta function admits meromorphic extension on the complex plane with a lot of zeros and possibly a lot of other zeros somewhere, according to a certain conjecture. But here I'm restrict myself to the real axis. Why? Because I could consider the complex extension and try to see if the real part and imaginary part of this extension, complex extension, meromorphic extension, could be definable in an o-minimal structure. But this is obviously wrong. This is not possible because this meromorphic extension has infinitely many zeros. So in an o-minimal structure, a definable function can have in one variable at most finitely many zeros. So this is why I'm restricting here to the real axis. Okay, question: is the structure generated by the zeta function o-minimal? Well, let's see a little bit. So the answer is yes, and yes, the answer has been given by Van den Dries and Speissegger in 1998. So what is the main idea of the proof? Well, the zeta function has a pole at the point 1. If I'm correct, it's a unique pole, and it is a simple pole. So, which means that it has the zeta function has a very regular behavior in the neighbor of this pole. So elsewhere on the real axis, it is on every interval it is a restricted analytic function. So the main problem is the behavior of this function at infinity. In order to study this behavior, we introduce the function h of x defined by zeta applied to minus log of x. So x here now has to be seen close to 0, meaning that minus log of x goes to plus infinity. And the zeta function applies to this variable at infinity. So I'm working with this function h here, right? So obviously, this function, the function zeta, which is equal to h applied to exponential of minus x, is definable in the exponential closure RH exp of RH, because it involves the exponential function here. So you have to introduce the exponential function to define zeta. Consequence of this elementary remark: if we can prove that RH is o-minimal, then by exponential closure that I mentioned before, R sub H exponential will be o-minimal, and so the structure generated by zeta will be o-minimal. So this is how we proceed. We focus on a structure which contains this function h defined in a neighborhood, a positive neighborhood of the origin. Am I reasonably clear? Does it make sense? Okay, little remark. Thanks to the definition of the zeta function, my new function h here, my auxiliary function, can be defined as such a sum, which is actually a convergent sum. By convergent, I mean that the family of monomials x to the power log of n is a summable family of functions on a positive interval close to the origin. So more precisely, H is a so-called generalized power series, generalized because it involves a real exponent instead of simply integer exponent. And so for short, I would call that a GPS. That will be my best joke of this talk. And it will converge, or being summable, on the interval 0 exponential of -2. So this function here is a power series, but unfortunately for us, it's a power series with real exponent instead of integer exponents. Okay, so we are going to study this class of function. So in view of o-minimality, we are going to study all the class of GPS, of generalized, convergent generalized power series, and try to mimic the methods of real analytic geometry and also commutative algebra to this family of convergent power series. So we will have some problems. For example, first problem, the ring of GPS in one variable is not Noetherian. Well, why? Because, well, its maximal ideal, which is generated by the power of x, the real power of x, is not of finite type. So we immediately lose Noetherianity. We lose, similarly, any kind of Weierstrass preparation with respect to these real powers. So we lose a lot of things. Well, what can I say? I mean, if you probably you watched this movie, as Robert De Niro says to Al Pacino in the movie, Scorsese movie, The Irishman, it is what it is. So we have to deal with that. So this is what I'm going to show you, how we can, very brief ideas of how we proceed here. So method of proof. So we consider the structure Rn star generated by all the convergent generalized power series. Okay, so what we are going we are going to proceed here to an adapted version of resolution of singularities for these functions with real exponents. So let me show you a very simple example. It's so simple that it's almost insulting, but I mean, anyway, it gives some ideas. Consider the function f, which is of xy, which associate to xy, x alpha minus y to the beta. Imagine that alpha and beta are positive real exponent, non-integer. And proceed to what I would call a generalized blow-up. So first, consider f applied to x and x power alpha over beta times y. This gives you x alpha by an obvious computation multiplied by 1 minus y minus y to the beta. So this here, if x and y are small variables, is a unit. It's a function which is a unit. So actually, this is a monomial form here. So you have proceed completely for this function to monomalization in this chart of the blow-up. Consider the other charts of the same blow-up. That is, consider f applied to y to beta to the alpha over alpha times x and y. You get similarly y to the beta times x alpha minus 1, which is also a monomial form. And if you work at finite distance in the blow-up, you have f of x and x power alpha over beta multiplied by lambda plus y, which you can expand here. You can expand this sum raised to the power beta via binomial expansion with a real exponent. So what you will get is actually x alpha multiplied by now here a series, a convergent series, but with integer coefficient. This is what you get here. You do not monomialize in one shot here, but you get a much better function because one variable which was generalized become a variable, let's say an analytic variable. That is a variable with integer exponent. So such a function is called a mixed function. And though you are in a better situation to go further now. And with all the analytic variables that you can produce via this kind of going up, you proceed to the classical techniques that you all are familiar with in resolution of singularities for these kind of variables. And at the end, you win. You can monomialize every function. So this is very shortly the plan of this method. And then once you succeeded in proving a version of local resolution of singularities here, you prove by geometric methods a version of Gabrielov theorem of the complement. I wrote Gabriel here, which is a bit too short. It's Gabrielov, obviously, of the complement for what I call sub-generalized sets. Well, with that, you have everything. That is, you can prove the model completeness of this second statement is the model completeness of the structure. Finally, thanks to that, you have the o-minimality of the structure, hence the o-minimality of its exponential closure, and hence, again, zeta, which is definable in this exponential closure, is definable in an o-minimal structure. And this is what I wanted to prove for the zeta function. Well, actually, this single slide here contains very briefly, in a very short way, it's the content of quite a lot of papers dedicated to proving that such or such structure is o-minimal. Actually, a first part is a version, usually a version of resolution of singularities which works in the structure you want to consider. And then secondly, a version of Gabrielov theorem of the complement adapted to the object of the structure you are studying. And these both statements implies o-minimality. So this is how one can prove the o-minimality of zeta, to be short. Okay, so now let's consider another function. And again, it was announced in my abstract. So now the famous gamma function, which is given by this integral. Okay, again, I restricted for similar reasons to the positive real axis. Question: is the structure generated by this restriction of the function gamma o-minimal? Answer: we'll see. First, again, the gamma function on this integral has a pole at the origin, is a restricted analytic function on every closed interval, compact interval of the real axis, of the positive real axis. So the main problem is at infinity. But we're lucky here because there are a lot of books of special functions which study in great details the behavior of the gamma function at infinity. So more precisely here, what we need is a formula called usually Binet formula from the French mathematician Binet, which gives you an expansion of the logarithm of the gamma function, which is the following formula. First, we have this expansion, which involves the logarithm function and a polynomial linear term here, plus here a remainder, which is actually given by this integral. I'm not going to explain it in detail. So let's believe this formula here. So let's give a name to the remainder. I call it phi applied to the variable 1 over x. Remember that in this formula here, we mean that x goes to infinity. Now phi, as it is applied to 1 over x, I see it as a function in the neighborhood of the origin, of the positive neighborhood of the origin. Let's call phi the Binet function. Binet as Binet here. Well, it has been proved that R augmented by extended by this Binet function is o-minimal. Hence, again, by exponential closure, R phi x is again o-minimal. It's o-minimal as well. So the gamma function, as it is by this formula definable in this exponential closure, well, it is definable in an o-minimal exponential closure expansion of the real numbers. Okay, consider now, so a few words of the proof, this Binet function phi here, which is related to the remainder of the Binet expansion of gamma, of log of gamma at infinity. Well, everything is known about this function. I mean, it is written in books, in classical books, some of them from the 19th century. So this function phi here is defined and C infinity on a small neighborhood of the origin. It is analytic on the open neighborhood, that is when you remove 0, but it is not analytic at 0. But, and that's the important thing, the Taylor, it is C infinity at 0, so it has a Taylor expansion at 0. But this Taylor expansion is divergent, which explains why phi cannot be analytic at 0. So it's a divergent Taylor expansion here. But, so that's a bad feature to have a divergent Taylor expansion. But there is now a nice feature. Phi is a so-called Jeuvret function. So if you are not so familiar with this notion from analysis, let me briefly explain them to you. A Jeuvret function is the sum via an appropriate summation process of its divergent Taylor expansion at 0. So let's try to be clear here. So the divergent expansion, the Taylor expansion, sorry, is divergent. So you cannot sum it by usual methods. But you have the possibility of associate, nevertheless, a sum to this divergent series by a more involved process, which is due to Borel and Laplace, the beautiful hours of French analysis. Okay, so for such a function f, if the Taylor expansion vanishes, then it implies that as the sum is given by this morphism of summation, that the germ itself at 0 vanishes. Such a property is called quasi-analyticity. That's a fantastic property. So in some sense, it's the best thing you can hope without analyticity, if analyticity doesn't work. So from the point of view of o-minimality, this is great, because thanks to that, you will do on the formal side, that is on the side of formal power series, you can perform formally to your preferred algorithm of resolution of singularities on the side of formal power series. Okay, but thanks to quasi-analyticity, this algorithm will how can I say, lifts on the side of germs, meaning that you are able to monomialize the germs, the Jeuvret germs as well. And this is what we do here. And thanks again to this monomalization process, as in the formal class for the zeta function, well, again, you can conclude that the structure Rg generated by the Jeuvret functions is o-minimal, and hence is exponential closure is o-minimal, and hence again, gamma being defined is defined in this o-minimal structure. So if you are not completely lost, we have proven so far that gamma and zeta, or more precisely the restriction to the real axis, or real interval of the real axis, both of these functions are definable in an o-minimal structure. So these results has been obtained by basically by Speissegger and Van. So at the time of the presentation of these results, a question was quickly raised. Are they definable in a common or minimal expansion of the real field? And that's not obvious. That's not obvious. So the thing is, do we really need to build two structures adapted to each of these functions, or could we just consider a single o-minimal structure which would contain, if I can say so, both of these functions? So that's an old question, and this is exactly the question we have answered in a recent work with Tamara Servi and Patrick Speissegger. Okay. Now, why is it not so obvious? Well, one thing which could happen is that each of these functions could be definable in the structure of the other function, if you see what I mean. But it's not the case. It's not the case. For example, zeta is not definable in the structure algebraic extended by the exponential function. It doesn't work. Why? Because if it worked, it can be proved by some technicalities that the function zeta of minus log x, remember that it is my first generalized power series here, with the exponent being log of n, this function would belong to a finitely generated semigroup of the positive reals. And it is obviously not the case because the exponents are log n. They do not belong to a finitely generated semigroup, meaning that zeta is not definable in the exponential closure of the Jeuvret structure. Similarly, gamma is not defined in the exponential closure of Rn star, which is the GPS structure, the generalized power series structure. Why? Because if it was the case, its Taylor expansion, more precisely, the Taylor expansion of the Binet function would be convergent. And if you remember what I said, it is not the case. The Binet function is not, the Taylor expansion of the Binet function at 0 is not convergent. So it cannot be the case. So each of them does not belong to the structure of the other one. Well, we could expect the result à la Grothendieck. Well, they could belong to the vastest o-minimal structure if such a thing existed. But it is not the case either, because such a thing does not exist. And why is that? That's an amusing thing. Why does not such a thing exist? Well, it's because we can produce examples of incompatible o-minimal structures. That is, pairs of o-minimal structures which do not admit a common o-minimal expansion. So let me show you briefly an amusing example, which was produced by myself and Fernando Sanz and Reinhard Schäfke in 2007. Consider the following vector field of the three-dimensional space. So x dot is equal to x plus y minus z. Y dot is equal to minus x plus y. And z dot is equal to minus z squared. So you have here a polynomial, almost linear, if I can say so, vector fields. Very simple. To understand it a bit better, consider the complex variable u equals to x plus y plus iy. So the vector field can be expressed as a differential equation in this variable in the following way. It is equivalent to say that z square u prime is equal to 1 minus I times u minus z. So this is a so-called saddle node Euler differential equation, but a complex version of the original Euler's differential equation. Okay, so what's happening now? Well, every single trajectory of the node part, it is a saddle node equation, of the node part of this vector field is actually definable in an o-minimal structure. So the picture is the following one. Again, remember that I am not Michelangelo, so I apologize in advance for what I'm going to do now. Well, so this is, let's say, the positive quadrant of the real three-dimensional real space. So every trajectory of the vector field here in this quadrant, starting from any point here, goes down, is attracted to the origin. So this is not oscillating at all. It goes quite directly here. So every trajectory does that. Okay. So we proved in 2007 that every trajectory is definable in o-minimal expansion of the real field. But the amusing thing is the following one. Pairwise, two trajectories cannot belong to the common o-minimal expansion of the real field. That is, pairwise, the behavior, so it's very hard to draw, actually, beside the fact that I'm very impaired on this matter. Pairwise, they do something like that. They spiral, each of them spiral around each other of them, but still, each of them goes quite straight to the origin here. Am I clear here? Even on the computer, it's not easy to draw this phenomenon. You see more or less nothing, even if you zoom a lot. So what does this example produce? It produces an infinity, a vast infinity, as Grothendieck said, of incompatible, an uncountable infinity of incompatible o-minimal expansion of the real field, meaning that there is no such a thing as a vastest o-minimal structure. So for my structures here of interest, that is the structure related to gamma and the structure related to zeta, a priori, I know nothing. I cannot consider as granted that there will be a common o-minimal expansion of those. So this is the result I wanted to show you. I'm coming to that. Do you give me 1 or 2 more minutes just to show you my results?
Yes, yes.
Okay, I won't be long, I promise. So the result we produced recently with Tamara Servi and Patrick Speissegger is the following one. Precisely, it consists in what we call, which is probably the title of the paper, by the way, what we call amalgamating gamma and zeta. Well, you can guess what the statement is if you followed me a little bit. So there exists a collection G star of algebras of functions such that the structure generated by these by these function of G star is o-minimal, first thing, and moreover, the gamma function and the zeta function restricted to the positive real axis are both definable in this expansion. So that's the main theory. So they are compatible. So you see, it took some time to prove it, and actually what we did. So yeah,
just a question.
Sure.
There exist collections.
Yeah.
Is so it's a bit imprecise because is means that there is one function. So
no,
what do you mean by collections of?
Okay, I mean by collection I mean nothing. I mean a set, but they are algebras of function. I mean for every dimension m, there is an algebra of function G m, an algebra of function which go from Rm to R. This is what I mean.
Okay.
Okay, as similarly to the real analytic functions or the generalized analytic functions. Is it clear now?
Yes.
Okay. So this is what I mean here, but when I say a collection of algebras of functions. For each dimension, we have an algebra of function. So, and the total family of these algebras of function generates an o-minimal expansion of the real field. And again, gamma and zeta both are definable in the exponential closure of the structure Rg star. So in a few words, the idea, and then I promise I stop. So reminder of the situation. First, zeta is related to the GPS, the convergent power series with real exponents. Second, and this is these functions generate the structure called Rn star. Second, the gamma function is related to Jeuvret functions. Remember that Jeuvret functions are smooth functions with possibly divergent Taylor expansion at the origin, but with the formidable quasi-analyticity property. So what I mean here is that these two functions belong to quite different universes. So our idea was to mix these two universes together in some sense by considering here, by developing a theory of functions whose germ at zero has a possibly divergent generalized asymptotic expansion. That is an asymptotic expansion, which is not a Taylor expansion anymore, because it could contain some real exponents. So this is what I call it an asymptotic expansion, and not a Taylor expansion. So we develop a theory of function whose germ at zero has a divergent generalized asymptotic expansion, and also a quasi-analyticity property. Though this sentence mixes the two properties of these two different structures. And this is what we did. We developed this theory of these functions such that if the asymptotic expansion is zero, then the function itself vanishes. And we proved that both gamma and zeta belong to the exponential closure of the structure generated by these functions here. Having first proven that this collection of functions here generates an o-minimal expansion of the real field. And the rest is quite technical, so as it is already late. Oh, I see that somebody raised his or her hand.
Yes, sir. Yeah,
yeah.
It is me. Yeah, okay, yeah. Just I have one question. I didn't get you well about this theorem. Can you explain more about the idea of this theorem, please? Sorry. Thank you.
Sure. So, okay. Well, actually, it's up to you. The fact is, my time is over. So I obey to the chairman, which seems to be Kevin.
That's okay for me.
I mean, so can I ask for 5 more minutes in order to answer this question?
Yes, sure.
Okay, so I apologize if I have been a bit long, but the question is asked, so I cannot I cannot avoid the obstacle. Okay, so in order to build this new class of functions, that is, remember, functions with a divergent asymptotic expansion with real powers and with the quasi-analyticity property, we actually considered the following construction, which has been inspired to us by Tougeron, a French geometer and analyst, in one of his papers from 1994, and which also inspired the previous work on GPS by Van den Dries and Speissegger. So you have to, I mean, if you want to remember something, there is a very important principle here about quasi-analyticity. That's the kind of, this slide is more meta-mathematic than mathematic. So an element F of a quasi-analytic algebra of real function. By real function, I mean defined on the real axis and real valued. An element of such a quasi-analytic algebra, so the important word here is quasi-analytic, appears often. So I have been a bit precautious here. I mean, often if not always, as the restriction of the real axis of the limit or the sum of a sequence of complex holomorphic functions defined on shrinking complex domains. This is quite a general way to produce quasi-analytic classes of functions. So that is, I mean here that quasi-analyticity is not a real phenomenon. It is actually, as is analyticity, actually, it is a complex phenomenon. So in order to build quasi-analytic functions, you have to go to the complex plane, or even, if necessary, to the Riemann surface of the logarithm, and to build sequence of holomorphic functions of possibly shrinking domains, which would converge, or whose sum would be the functions, the real functions you want to study. So that's my meta-mathematical observation here. So in our situation, the good functions are the sums. They are not only holomorphic, but they are sums of complex generalized power series, convergent complex generalized power series. For us, these are the good functions. And the new one has to be, in some sense, limits of sequences or sum of sequences of such functions.
Do you add some restrictions, like
yes,
that
of course.
would be Puisieux?
Well, we had some restriction on the support, actually, here. You don't need Puisieux because the exponent alpha here are going to be positive reals, but we are going to add a restriction. We call that natural, meaning that for every real interval, you have only finitely members of the support of the series which belong to such an interval. So this is the kind of Puisieux-like restriction that we impose. Am I clear? Yeah, is it okay? Is there anybody here?
Yeah, yes.
Yes, okay. So I'm sorry to ask this question all the time, because you know what it is to be lonely online. Okay, so actually these functions are defined on the Riemann surface of the logarithm here. So when I say complex extension, I mean, well, truly complex extension, big, but on some domain of the Riemann surface of the logarithm. And then let me show you, and this will probably be my last slide, because you cannot kill me at distance, but I can kill you in some sense. Well, how do we build a Jeuvret function of our class, a generalized Jeuvret function? We associate to a Jeuvret function what is called a positive Jeuvret order, which is a real number, a positive real number. That is not an integer a priori. It could be an integer, but it's not necessarily an integer. Also an angle, theta, which is bigger than pi. That is the thing now, a sequence of bounded holomorphic functions such that these functions are defined on an open sector based on the origin with a radius r, which is fixed, and an opening which is given, which is fixed also, which does not depend on the index p, which is given by theta divided by 2k. Union a disk drawn on the Riemann surface of the logarithms of center 0 and with a radius, which is this one, r divided by 1 plus p raised to 1 over k, which is a shrinking radius when p goes to infinity. So basically, this function fp is defined as on what we call a sector disk. That is the union of a disk and a sector of some opening. And the disk here will shrink to 0 when p, the index p of the sequence, goes to infinity. So what is left fixed here is the sector. So we are going to build a function which is actually defined. So my function f will be defined on the sector, but the sequence fp is defined on the sector disk. But remember that the disk is shrinking when the index p goes to infinity. Okay, so this is considered as a subset of the Riemann surface of the logarithm, and well, fp, each function fp is the sum of a convergent GPS. And as I said before, we assume that all this family of function or of convergent GPS has a common support, which is called natural, meaning that every real positive real interval contains only finitely many elements of the support. Well, and also what I call a coherence condition. I'm going to spare you the detail of this. And f itself, the Jeuvret function itself, that the important part, this is the class that I want to build, is going to be simply the restriction of the interval 0r of the sum of the fp's. Meaning that actually, thanks to all these conditions, this sum exists. And this is the class of function we are going to build. So it's quite complicated. I mean, we spend a lot of time. So these ideas of working with sequences and series of holomorphic functions comes directly from Tougeron. And we are just inspire and generalize this idea by considering functions fp which are GPS instead of being simply holomorphic. Well, this is how we build the function. And we prove that thanks to all these complicated hypotheses, the class of the FPs is a quasi-analytic class of functions. Hence, thanks to the tools I briefly explained at the beginning, an o-minimal structure. So this is this construction, which is quite complicated, is our main work here. And it's not very complicated to prove that actually gamma and zeta are definable in the exponential closure of the structure generated by the function f here. So we denote this structure by Rg star. I have been very long here, so I guess it's now seriously time for me to stop. And I thank you for your patience, and I apologize.